Hi guys, this is Electric Tutor, and in this lesson 4, I want to cover trigonometric integrals. In particular, there's two types we want to work on. It's not just we're beyond the basic like single trig function integrations. And we're going to deal with combinations of trig functions. Let me just show you that first so that you can get familiar with it as soon as possible. We're going to work in particular with these two forms, combinations of sines and cosines, and combinations of tangents and secants. If we take a closer look at these two forms, now there's relationships between one another, like derivative-wise and integration-wise. Sine and cosine are like brothers, right? When it comes to this case, derivative of tangent is secant squared, and derivative of secant is secant times tangent. So there's some relationship there, and it seems like we could use u sub to solve these types of problems, and sometimes we do. If these powers are not very high, and we have basically convenient configurations, we can do that directly with u sub. But most of the times we can't. That's the purpose of this whole section, is for you to do an extra step before we go ahead and use u sub. In the end, when it comes to integrals, our goal is to always simplify the integral enough such that we can either use u sub or integrate directly and be done with the exercise. And u sub is just in of itself a form of simplification too. So that's always our end goal. In this video, we're going to work on this first type, and I'll make a follow-up video for this second type. Before we start with our first type, I want to show you the extra step you need to take before you apply the u sub. And that's basically just play a little bit with trig identities. So I would say that these 5 are the only ones you'll need for the two types we're going to work on, okay? Starting off with obviously the most fundamental one being this. You're going to use that quite often. And of course, this little variant, if we divide this whole equation by cosine squared, we would get this one. So those two are very important. The third variation, you don't really need it. Also, if you have sine squared or cosine squared and you need to reduce the power, there's power reduction identities, and these two are useful. Okay, I believe that for cosine squared there's like 3 different equations, but this is the only one you need. And finally, when it comes to double angle identities, there's this one, the sine version, and sometimes we do need it in case our arguments are different. This could be useful. Now, cosine 2 theta, we don't really use that one. There's like 3 different equations for it, and it just complicates things even further. But for this one, it does simplify the exercise a lot of the times, so it is useful. Now let's begin analyzing the first type, this one. Alright, so for type 1, remember that m and n, the powers, can be either even or odd, okay? 2 possible cases. So, and if you think of it, there's 4 possible combinations here. Either both are even, or both are odd, or 2 other combinations, right? So let's see, or let's look at the first one that says that n is uneven, which also means that m is even. Okay, so m is even and n is uneven. But let's focus on n. In other words, let's focus on when we have a cosine with an uneven power, like raised to the 3, to the 5, to the 7, so forth. Okay, so what we want to do is we want to set up this integral such that we can use u sub and be done with it, right? So the first step we do is we take one of the cosines out, as we can see here, and we're going to be left off with cosine raised to an even power. And if that power is higher than 2, in other words 4, 6, 8, so on, then you can split that into a cosine squared, and then the other factor, put it on the outside. It's basically the same thing, right? But it could be an extra step depending on what exercise you're working on. And the reason we want to do that, and I emphasize it, is because for cosine squared, we have an identity, right? The basic one, sine squared plus cosine squared of whatever is 1. So for cosine squared, we're going to use 1 minus sine squared. Okay? Use that, and the reason why we do that is because we can say then that u equals sine x, making du be cosine x dx. And I'm going to do it in another color. This is always going to be our du for this particular case. And this is going to be u, and this is going to be 1 minus u squared raised to some k power, even power. Okay? And that is how we're going to solve this particular case. Let's look at case 2. Case 2 represents a case where now the sine component is the one that's uneven, meaning that the n is going to be even. The cosine power is going to be even. So it's basically the opposite of case 1. Okay? So what happens if we have the opposite of case 1? What we're going to do is just play with the sine power instead of the cosine. We're going to leave the cosine alone, as you can see here. And again, we want to take one of the sines to the outside just to be able to make a du later on. And we're going to be left off with sine squared raised to some r power if applicable. And again, we want that because we want to apply this basic identity again. And that's why we see 1 minus cosine squared here. In this case, we can use u equals cosine x. And u is going to be minus sine x dx. So if we apply a minus here, then that along with this is going to be my du, right? And so this is going to turn into my u, and 1 minus u squared raised to the r even power. Okay? That is going to be case 2. We're left off with two more possible cases where both are even and both are uneven. When both are uneven, okay, for instance, cosine to the third times sine to the fifth or something like that, then we can use either case 1 or case 2 strategies. And my recommendation for you guys is to pick whichever has the lowest power. So as I said, if I have cosine to the third times sine to the fifth, and we're going to integrate that, I would typically go for this one. So in that case, that's going to be, let's see, case 1, because the cosine has an uneven power, and that's what we're seeing here, right? And finally, case 4. Case 4 is when both are even. When both are even, you're not going to be able to play the way you've done with cases 1 and 2. So what we want to do is apply, it says half angle identity, it should say double angle identities. Basically, the sine 2 theta equation. These are the 4 possible cases. Let's look at our first example. Okay, the integral of cosine to the third power. We don't see a sine here, so it seems as if this is not going to apply, but it really does. So this is technically what we named to be case 1. So the cosine has an uneven power. Our goal is to then take one of those cosines out, right? We're really left off with a cosine squared, so we don't We don't need to raise that to some r or k or whatever. And the next step was to make a substitution. So it's 1 minus sine squared times cosine x dx, and now we're ready for our u sub. So let u be sine x, so that du is cosine x dx. So this is du, and this is u, okay? So we're left off with the integral of 1 minus u squared du. And now the integral is just easy and straightforward. We go back to the x world, and we're done. It's not that hard, right? Let's do another example. Alright, so in this example, we can actually see a combination of sine and cosine. You can see that both have uneven powers, which is basically what we called case 3. When both were uneven, you were free to choose whichever of the two approaches you wanted, either case 1 or case 2. My recommendation, if you remember, was to use the one with the lowest power. That's usually easier, at least in my experience. So I'm going to pick sine cubed. So if I pick sine cubed, that means that I'm going to work on what I called case 2. Alright? And in case 2, we just rewrite the integral. In case 2, we wanted to take one of the sines to the outside, right? We're left off with the sine squared over here, cosine to the 7th, sine x dx. The next step was to make the substitution. So 1 minus cosine squared times cosine to the 7th. The rest is the same. Now we are ready to apply the u sub. So let u be, in this case, cosine, because our du can now be minus sine x dx. Okay? So sine x dx is du, well, minus du technically, and the rest is just going to be u squared and u to the 7th. And we can work on that actually. So 1 minus u squared times u to the 7th at the u, and don't forget the minus sign. Okay? That's going to be minus sine, of course, I have to distribute u to the 7th minus u to the 9th, which gives us, I'm also gonna distribute this sign. That's minus u to the 8th over 8th plus u to the 10th over 10. Always remember to go back to the x world, or whatever world you were originally in, and never forget the plus c. So we've seen a case 2, a case 1, and at the same time something that looks a little bit different. Let's do one more example here. So we're left to do something about case 4. This applies to a case 4 because both are even. And there's actually something here that I should correct. We can use double angle identities for case 4 if applicable, but we can also use power reduction, so for sine squared and for cosine squared, as we'll see in this example. Okay? Because how do we solve this if both are even? Well, the way to do that would be to rewrite the expressions. So sine squared, if we wish to reduce the power, it would be equivalent to 1 minus cosine 2x. This is one of the identities I showed you in the beginning. And the second one is basically 1 plus cosine 2x over 2 dx. Now it seems like we've complicated things further, but it's actually much easier, okay? Much easier. This is solvable. So if we do some arithmetic, there's a 1/4 that I can factor to the outside, and I'll be left off, let me rewrite this, I'll be left off with 1 minus cosine squared 2x dx. And now in this case, you might be tempted to turn this into a sine squared 2x. But, I mean, I guess you could do that, but in my case, I think it's easier if you apply once again the identity we used over here. In other words, you have 1/4, 1 minus, and then the identity once again, 1 plus cosine, and this now it's got to be 4x because it's twice the original angle. Cosine 4x over 2. And now this is an integral that we can solve. We just have to apply some arithmetic again. So again, if we do some of that, there's a 1/2 that we can factor. So 1/2 times 1/4 is 1/8. Integral of 1 minus cosine 4x dx. And we can just integrate that directly. We don't even need to use u sub. I mean, technically we do have to say that u is 4x, du is 4 du, but honestly, if we don't need to do that, because I know that the integral, well, let's just do it. So it's 1/8. Integral of 1 with respect to x is x, right? Minus the integral of cosine is going to be sine. So the integral of cosine is always sine of the argument over the derivative of the argument. That's the general form. If you remember that, then you don't really need to apply this, okay? You just need to remember that, hey, I have to divide it by the derivative of the argument. Okay? So plus c. That's whenever we see something that's different than 1x, right? Because if we have sine of x, derivative of x is just 1, right? So we're always technically dividing it by 1. We just don't think about it, but that's always happening. So don't forget the plus c in the end, and we're done. So as I said, there's going to be a follow-up video here for the type 2 cases. Be on the lookout for that, and I'll see you later. Thank you for watching.